Great, thank you. So like the other speakers, let me start by thanking the organizers, both for bringing us together to this wonderful place and putting together a wonderful program. So I feel like I've learned a lot over the last couple of days. The variety of talks has just been fantastic. And thank you, too, for giving me the opportunity to tell you a little bit about the work going on in my group at the University of Chicago. So I thought I would tell you a little bit about work we're doing in the general area of reservoir engineering or dissipation engineering. Work that we're doing to try to understand how we can stabilize interesting states of bosonic systems where we have some complexity. Complexity either coming from having many, many modes or from having strong nonlinearities. And the real goal is to try to come up with strategies that are compatible with experiments. So a lot of what I'll tell you is really motivated by ongoing experiments, both in the domain of circuit QED, superconducting microwave circuits, and the domain of quantum optomechanics. And there's two stories I hope to tell you about, sort of time permitting. The first is the idea of using symmetry to come up with very, very efficient, smart ways of stabilizing complex states of lattices, arrays of cavities. And the idea is that if you exploit symmetry, you can really get away by just controlling dissipation on one site of a lattice and get the whole lattice to relax into a state that's interesting. And the second story I'll tell you about, again, time permitting, is what can we do when we have strong interactions? What can we do when we have strong Kerr-type interactions? And I'll tell you about an idea for how you can actually stabilize entangled cat states in two remote cavities. And the nice thing there is, well, look, the cavities can be remote. The resources that are needed are completely in keeping with what can be done in circuit QED. The other nice thing about this problem is it's actually an example of a driven dissipative nonlinear problem that you can solve exactly. Okay, so this first story I'll tell you about the lattices, that was done with a postdoc, I guess now a former postdoc, Henri. And the second story I'll tell you about was done with Misha Mamayev, who was a student of mine at McGill, and Luke Gavaya, who was a postdoc of mine up until about 2 weeks ago. He's now at BBN Raytheon. Okay, so the context for all of this work is this general idea of reservoir engineering or dissipation engineering. Here's the cartoon version of what the big picture idea is. We start with some system that is in some boring state. We'd love it to be stabilized in some interesting state or maybe in some interesting manifold of states. And the cartoon idea is, could we construct some kind of interesting dissipative reservoir such that when this system interacts with that dissipative reservoir, the reservoir stabilizes it into some interesting state. So if you could make this cartoon reality, that would be wonderful. You would get your interesting state in the steady state, not at just some magic time given by some coherent unitary evolution. And also, in principle, you would get this interesting state irrespective of what state you actually started with. Okay, so I think, as most people in this room probably know, you can also very usefully at times think about this strategy of reservoir engineering as autonomous or coherent feedback. So in a way, by trying to design protocols like this, you're trying to design a system whose internal dynamics mimics a perfect measurement plus feedback operation. Okay, so clearly, if you can do this, there's some pretty amazing advantages. The key question for all sorts of reservoir engineering schemes is, how do you actually construct this non-trivial reservoir? And of course, there's a question at the level of theory. There's even a harder question of how do you come up with an idea that someone could actually implement in the lab. So there are many, many recent examples of reservoir engineering being employed in the quantum regimes, in systems with a few degrees of freedom, experiments in circuit QED, in atomic systems, traditional cavity QED. I'll just tell you about a couple of recent experiments in an area we haven't heard too much about at this workshop, and that's the area of quantum optomechanics. And these are experiments where we were involved at some level on the theory side. So in a nutshell, what's optomechanics? Optomechanics is having the motion of some large mechanical object interact with photons in a driven cavity or photons in a driven circuit. This is the basic cartoon, Fabry-Perot cavity, where one mirror can actually move. That's your mechanical degree of freedom. So in this kind of system, if you want to do reservoir engineering, the object that you might want to put in an interesting state is the mechanical resonator. The natural degrees of freedom to use as the engineered reservoir, those would be the photons in your driven cavity. So the most obvious thing you could do is you could do laser cooling. You could use the photons in the cavity to look like a zero temperature bath, put your mechanics in the ground state. But there are more interesting things you can do, and these have been done recently in experiment. So just by driving the cavity with two tones, just sending in coherent light, you can actually trick the mechanics into thinking it's interacting with a squeezed reservoir. And using that idea, you can actually stabilize the mechanical state into a quantum squeeze state, a state where one quadrature of motion is actually squeezed below the 0-point variance. Okay, so that's actually been something that's been done now in 3 different experiments. You can even go further with the exact same kind of system. Imagine you have a cavity that's actually coupled to 2 different mechanical degrees of freedom. Again, with this very, very simple kind of driving, just drive that cavity in just the right way with 2 coherent tones. You can actually have the cavity photons act like a non-trivial dissipative reservoir that wants to stabilize the 2 mechanical modes into an entangled state, into a 2-mode squeeze state. Okay, and that's also been done very recently in a circuit optomechanical experiment from Mika Salampa's group in Finland. And here, the mechanical objects are these capacitor plates where the top plate is actually free to vibrate. Okay, so we know this reservoir engineering. It's a great strategy in optomechanics when you have 1 or 2 modes. It's a great strategy in other systems. What if we actually go to systems with many modes? And this isn't just a kind of fun question to play with theory. There really are now experiments in a variety of different systems where this is a timely question to be asking. So here's an experiment from the domain of circuit QED, an experiment from Andrew Houck's group at Princeton. So what are you looking at here? You're looking at a lattice or an array of microwave coplanar waveguide cavities. So each one of those squiggly lines inside that box, that's one of your cavities. This structure here actually forms a very interesting kind of lattice structure. It forms a Kagame lattice. Here's an example coming more from the realm of optomechanics, an experiment from my former colleague Jack Sankey at McGill, where you basically have an array of these silicon nitride trampoline-style resonators. Okay? And so again, the kind of question is, how do you use reservoir engineering ideas to get interesting states of these lattice bosonic systems? Okay, so clearly this is something that people have thought about for a while. There's a lot of beautiful work that's been done by a number of people, I'm sure people in this room. There are many, many works coming from Peter Zoller's group, for example, and collaborators of Peter's. And often the approach that's taken, at least at the level of theory, well, look, if I want to get the entire lattice to be stabilized in some interesting state using dissipation, I need to control dissipation everywhere. So here's one example, right? So an example from Peter's group where you have a 1-dimensional array of photonic cavities. The goal is to stabilize it in some kind of state that mimics a Bose-Einstein condensate, a state where you have long-range phase coherence. And so what this cartoon is meant to show is, well, the way this is going to work, as described in this paper, is you're going to try to control the dissipation on each link in this 1-dimensional lattice. So at the cartoon level, okay, so you have some specially controlled dissipation on each link. Maybe that doesn't look too bad to you. What does it actually involve? Each one of these green boxes requires 2 mechanical modes, 1 optical mode, an additional photonic cavity mode, and 2 drive tones. Okay, so clearly it's amazing that these schemes work. It's a really, really nice piece of theory. Taking that to an experimentalist and saying, hey, do you have modes to spare? Do you have drives to spare? Can you realize this? This is not the easiest thing in the world to implement. Right? So the thing that would be beautiful is, could we get interesting physics not by trying to replicate this kind of cartoon, where you engineer dissipation everywhere, but if we could sort of implement this sort of cartoon. So this is meant to indicate some kind of 2-dimensional array of cavities. That's what those circles are. And then the idea is, what if we just control the dissipation in an interesting way on just one site? Right? Is that going to be enough to do anything interesting? Right? And how do I know when this sort of strategy will give me something interesting? Okay? And so this is clearly not impossible. And the thing that really got us thinking about this problem was a paper from a few years ago from Zappilli, G, and Vitali, where they work out in detail a specific example where this kind of strategy works in a way that to me was really, really surprising. So what's the simple example they looked at? You have a 1D array of cavities, described by a simple tight binding model, so photons can hop from site to site to site to site. You stagger the on-site energies. So if you want, you play with laser detunings. So the detuning on site 1 is negative, the detuning on site -1. And then the only controlled dissipation is at site 0. At site 0, you couple to a squeezed reservoir. Okay, and so what they show is, in this setup, you actually get stabilized into a pure entangled state. And what's the entanglement? It's a product of two-mode squeezed states, two-mode entangled states in real space. Mode 1 is perfectly entangled with mode -1. Mode 2 is perfectly entangled with mode -2, et cetera, et cetera. Okay? And again, depending on how much you've sort of thought about this, maybe this is not surprising to you, maybe it is surprising. What would you generically expect in this situation? So generically, what are you doing? Oops. This squeezed reservoir is sending in photons on that middle site. It's sending in paired photons. The photons are coming into the lattice. They're moving around. Eventually going to leave, again, through this port. The generic steady state you'd expect is, in your steady state, you're going to have some flux of photons leaving from the lattice going into that reservoir. Generically, you'd expect an impure steady state of the lattice, because there's some correlation between the lattice and what's going out. Okay, and in this special example, that doesn't happen. You relax into a steady state where basically nothing is coming out of the lattice into that one-engineered reservoir. And the lattice has a photon population, and there are these entanglement correlations. Okay, so very, very nice, a really nice specific example. The natural thing to ask is, well, you know, could you do this in other settings? What's the special sauce, if you want, in that example that really made it work? And could we extract it and use it in other settings? Okay, so the most general setting you could think about, still keeping our resources required fairly simple. Imagine I have some arbitrary array of cavities, right? Maybe in 2-dimension, maybe disordered. I have photons hopping around between these different cavities, these circles. It's described by some simple tight binding model. So there's some terms that describe photons moving from site to site. There are some on-site energies. Okay, and then what's a simple engineered reservoir? Well, we'll do the same thing as in that Zappilli example. Let's imagine that we single out one of those sites and we couple it to a squeezed reservoir. So why is this a good thing to look at? Well, A, it's a simple thing to look at, right? This is almost the simplest non-trivial reservoir you could think about. And also, we know how to build this kind of reservoir in a variety of experimental situations. We know how to build squeezed reservoirs in circuit QED. We even know how to do it in optomechanics, those examples I told you about earlier. Okay, so how would you describe this theoretically? You have your simple tight binding Hamiltonian. You have a master equation that now includes dissipation on that one site. This is that simple Lindblad dissipator for a squeezed reservoir. So that squeezed reservoir, its jump operator is a linear combination of removing and creating a photon on that one site. This is the standard description of squeezed dissipation. I could also describe this using a quantum Langevin equation, a Heisenberg-Langevin equation. So here is my standard coherent Heisenberg equation. Here are the dissipative terms. There's the damping on that one site that we've chosen. And then there's the noise terms associated with that damping. And that noise has correlations that encode the squeezing. Okay, so the general question is, when does this lead to something interesting? A non-trivial pure steady state. So this is also a question that we're not the first people to think about. And there's a very nice paper from some people who are in the audience, so from Ma, Woolley, Ian Peterson, Naoki Yamamoto, where they really looked at this problem from a much more formal linear systems kind of control point of view. And they did something that was really, really impressive. They enumerated, basically parametrized, all of the possible steady states that you could get from this kind of setup. Okay, and I could impress you by showing you the complicated equations of parametrization they have. We felt there was still something left to do here, right? So if I'm talking to an experimentalist who comes to me with a Hamiltonian and says, is this Hamiltonian going to work? What is the basic physical principle that allows this kind of setup to give me this interesting state or doesn't allow that to happen? It's really hard to extract it from this really nice formal parametrization. So we wanted to look at this maybe from more of a, let's say, a physics perspective than a mathematical perspective. Is there a simple recipe or a simple physical principle that tells me when this is going to work. Okay, and the good news is, yes, there is a simple physical principle. Otherwise, I'd have nothing to tell you. There's basically two ingredients that you need to make this work. One is really, really trivial. One is a little less trivial. So what are the two basic physical principles you need to get this kind of setup to give you an interesting, pure, steady state? So the first one is sort of obvious. The first one is we better not have eigenmodes of my system that don't talk to the dissipation at all. Okay, so clearly this is a simple quadratic Hamiltonian. You could diagonalize it in terms of some eigenmodes. Those eigenmodes have wave functions. If I have an eigenmode that has a node at the site where I have dissipation, well, clearly game over, right? That mode will never see that dissipative environment. You're never going to be able to get it to relax. So the first kind of obvious thing, right, is you need to design a system that doesn't have wave function nodes in its eigenmodes at the coupled site. Okay, so that means generically you don't want degeneracies in the spectrum of your Hamiltonian, because then you could always factor that degenerate subspace into dark modes and to bright modes, right? It also means that if you have something like inversion symmetry, you don't want to put your dissipative site at that center of inversion, because then you'll have odd parity modes that will always vanish. So this is sort of an easy, obvious condition. This is one that's fairly easy to avoid by designing your Hamiltonian correctly. And I'll give you specific examples a little bit later in the talk where we really can avoid having any of these nodes at the position where we've attached the squeezed reservoir. Okay, so the more interesting condition and the more interesting question is, what if you've avoided having any of these uncoupled modes? So all of your eigenmodes talk to the squeezed reservoir. How do I make sure those coupled modes actually relax into a pure state? Okay, and again, the generic problem is you'd expect that you're sending photons in, photons are coming out. In the steady state, there'll be a flux out of the lattice into this reservoir. There'll be entanglement between the lattice and the reservoir. Your lattice will not be pure. So how do I avoid that? And the really nice thing especially coming from a condensed matter background, is that thinking about this problem from the point of view of symmetry, the kind of symmetry that we use to think about lattice models in condensed matter, really turns out to be the important key. So it turns out that the thing that we need for our Hamiltonian is we need it to sort of satisfy what we call a generalized chiral symmetry. So what does this mean? I have my Hamiltonian matrix in real space. Okay, if I have n modes, this is some n by n Hermitian matrix. It needs to satisfy a chiral symmetry. That means there needs to be some unitary matrix sigma that maps the Hamiltonian onto minus its complex conjugate. Okay, and this might sound like a very strange kind of symmetry to think about. It's actually one we think about all the time. So this symmetry guarantees that the energy eigenstates of your Hamiltonian come in pairs, E and minus E pairs. So this is one of the requirements we need. The other requirement we need is that whatever the symmetry operation is, it should leave the site where you've coupled the dissipation invariant. Okay, so basically, if you fulfill these two conditions, and if you have no dark modes, you're guaranteed to have a pure steady state. It's even better than that. Okay, so now we know what's the recipe. We tell our experimentalist friends, you need to construct a Hamiltonian with the right symmetry. It's even better than that. Once you have this symmetry, the steady state is essentially completely dictated by the symmetry. All the other details of the Hamiltonian are irrelevant. So what do I mean by that? So at the end of the day, what's the steady state we're going to get? It's going to be some Gaussian steady state, right? We're just talking about linear dynamics here. So the steady state will be characterized by some average photon number on each of those lattice sites. And so the first really nice thing is that the average photon number is completely uniform on all sites. Okay, so the average photon number is set by this squeezing parameter R, which is just set by the strength of the squeezing that you're sending in from that dissipative reservoir. So this is already a little bit remarkable because, again, I'm not saying that there's any translational invariance or any other symmetry in this Hamiltonian besides this chiral symmetry. So irrespective of any other details, you're always going to have a completely uniform average photon number. And then what about the correlations, right? The thing that tells me, hey, there might be something non-classical about this state. The only correlations that are non-zero are these two-mode squeezing correlations, so a product of two lowering operators. And what determines that? Well, again, it's set by how much squeezing you have. Clearly, if you have no squeezing, there's no correlations, there's no photons. But then, what is this correlation matrix? It's just the same matrix that generates your symmetry. Okay, so once you've constructed a Hamiltonian that has this chiral symmetry, and once you decide how much squeezing you're going to couple to, that really dictates the properties of the steady state. Okay, so again, not everyone, I'm sure, has spent a lot of time thinking about this symmetry, so this might seem like some wacky thing that maybe is not so physically relevant. The thing I want to tell you is that this symmetry is a very, very, very common symmetry. And let's think about the simplest situation. The simplest situation is when this real space Hamiltonian matrix H, where you can find a gauge where it's completely real. So this is what condensed matter physicists call time reversal symmetry. So in this case, I just have a unitary that maps H to minus H. So if you want, there's a unitary that anti-commutes with the Hamiltonian. This is a very, very common lattice symmetry. So we often call this in condensed matter as well a sublattice symmetry. So things like the graphene lattice structure, the well-known SSH lattice structure, they all have this symmetry. It's even better than that. You can have completely disordered models that have this symmetry. So imagine I have photons hopping on some lattice. So here I've drawn a square lattice. It could be anything. But imagine all of the hoppings were completely random, right? So the J's that connect one site to its neighbor, drawn from some distribution. That model is guaranteed to have this chiral symmetry. Okay? So how can I see that? So in this kind of structure here, it's a bipartite lattice structure. So I can label half the modes B, half the modes A. If I have nearest neighbor hopping, even if it's completely random, the hopping only connects A sites to B sites. Right? So then what's the symmetry operator? How do I take H to minus H? I just basically flip the sign of all the B sites while keeping the sign of the lowering operators for the A sites fixed. So because the Hamiltonian only couples A and B sites, and again, I don't want this term in this case, the whole Hamiltonian changes sign. Okay, so this is a very, very generic symmetry. It shows up in a lot of different cases. It's even a symmetry that exists in the presence of disorder. Okay, and in principle, that's a good thing. If our experimentalist friends can't build their lattices perfectly, there is a kind of tolerance to certain forms of disorder. Okay, so let me tell you a little bit about how this actually works, or why does chiral symmetry actually matter in this case. So let's think about the simplest situation where we have two modes, right? So what does it mean to have chiral symmetry? It basically means once you diagonalize your Hamiltonian, right, one mode has energy epsilon, the other has energy minus epsilon. Okay, so let me think of this Hamiltonian in terms of quadratures. So I could write my lowering operators in terms of x and a p. And then I could take the sum of the x operators for the two modes, the difference of the x operators for the two modes, and have these joint quadratures x plus, x minus, p plus, and p minus. Okay? So then this is the kind of structure the Hamiltonian has when written in terms of quadratures. And this is sort of it's becoming a kind of famous Hamiltonian these days. So Moncke has done some nice work on this. Eugene Polzik has done work on this kind of structure. It's something you can really exploit in the context of quantum measurements. Here, we're going to do something different with it. So what's so interesting about writing the Hamiltonian like that? Well, basically, if I do any sort of two-mode squeezing operation, so that is, if I squeeze the x pluses and amplify the x pluses, squeeze the p pluses, vice versa, the Hamiltonian looks exactly the same. Okay, if I want to think of that in terms of a Bogoliubov transformation, if I do any two-mode Bogoliubov transformation on A1 and A1 bar, no matter what I pick for the squeeze parameter or what I pick for that angle, the Hamiltonian looks exactly the same. Okay, so what does that mean? It means that there's many, many different ways to diagonalize this Hamiltonian. Okay, and why is that relevant to our problem? Well, when I couple one side of this lattice, let's go now to n modes, to the dissipation, this is what the coupling to that dissipation looks like. So this is the degrees of freedom of the one site that are involved, the lowering operator and the raising operator for that site. And here's the coupling to, if you want, the vacuum noise coming from that bath. Okay, so the problem in general is this coupling involves both destroying a quanta and creating a quanta. Even if I try to transform into the basis that diagonalizes my Hamiltonian, I'm still going to have, if you want, a cooling process and a heating process. So the nice thing about having this chiral symmetry, there's so many different ways I can diagonalize the Hamiltonian. So I can always find a way to diagonalize the Hamiltonian, find some choice of eigenmodes of the Hamiltonian where the coupling to the bath just looks like cooling. Okay, and you can't do that generically. There's a more formal proof in our paper, but heuristically, in a bosonic system with chiral symmetry, there's an infinite number of ways to diagonalize the Hamiltonian. You can always find a basis to make things look just like simple cooling. And once you have this simple cooling kind of picture, a bunch of Bogoliubov modes coupled to zero temperature noise, you're guaranteed to get a simple steady state where all of those beta modes are in vacuum. Okay, so let me tell you an example of sort of implementing this where things get even more interesting. So it turns out, so using this idea to get interesting steady states, life gets even more interesting if you give me a Hamiltonian where I can't get rid of the phases. So what I mean by that, again, is what condensed matter physicists call broken time reversal symmetry. So there's no way to make a local gauge transformation that eliminates the phases in my real space Hamiltonian. And so generically, if I'm talking about photons moving around on a lattice, this means that we're, in a sense, describing photons moving in some kind of synthetic magnetic field. Okay, and this is not a crazy thing to think about. So this is something that my colleagues at Chicago, Dave Schuster and John Simon, have realized recently in the domain of circuit QED. So they have a very, very nice experiment where you have a square lattice of microwave cavities. Basically, by introducing little Yig spheres, ferrite particles, on one out of every 4 sites of this lattice, they can basically generate this kind of tight binding model where when you go around one of these square plaquettes, there's some net effective Aharonov-Bohm flux. Okay, so this is a realization of the well-known Hofstadter model of particles moving on a lattice in some net magnetic field. So what does that look like at the level of some of our Hamiltonian? Again, I just have nearest neighbor hopping on a square lattice, but now there's some phases here. There's a phase associated with hopping in the vertical direction, and that phase factor depends on position. Okay, I'm going to take the special case that's the one that they realized in the experiment where the flux sort of going through that little square plaquette corresponds to a quarter flux quantum. So this phase is basically pi over 2. Okay, so why is this interesting? Well, when you think about the chiral symmetry involved, now it's this generalized chiral symmetry, or if you want, you could even think of it as a particle hole symmetry. So now the symmetry that we're thinking about has to take h, not just to minus h, but to minus h star. So the idea is that phases matter, and that's going to give us the ability to get far more interesting states. Okay, and one way of seeing that is if you diagonalize your Hamiltonian, if you diagonalize h in terms of eigenstates, and you write out this symmetry operator in terms of the wave functions of those eigenstates, this is what it looks like. So this is the eigenstate for some mode with energy E alpha. This is the wave function of the mode with the opposite energy, minus E alpha. Okay, so great. It's easy to write that thing down. What's interesting when you have broken time reversal symmetry? Well, you can't stop me from changing the overall phase of my eigenstate wave functions. And so when I do that, this symmetry operator is going to look different, right? If I decide to take a different overall global phase for each of my eigenstates, this thing will not look the same anymore. Okay, so there are actually many, many different, if you want gauge equivalent, chiral symmetries that are relevant here. So that seems like a problem. It's not a problem because the chiral symmetry that's relevant is basically picked out by where do I choose to put the coupling to the squeeze dissipation. Because again, one of my requirements is not only do I need this symmetry, the symmetry needs to leave the coupled site invariant. Okay, so now life is interesting. There are many, many different chiral symmetries. And again, the symmetry operator determines your steady state. Where I choose to put my controlled dissipation will pick out the relevant symmetry. So just really quickly to show what happens here, and we even did a smaller lattice in sort of our theory paper than what they realized in the experiment. So here's basically a 9 by 9 array of cavities with, again, this synthetic magnetic flux, pi/2 in each plaquette. So imagine I decide to couple my dissipation to a site that has a fair bit of symmetry. So this structure here, if I do a reflection about the y-axis, it looks the same. So if I put my coupled dissipation on that reflection axis, what does my steady state look like? Well, the relevant chiral symmetry operator is very simple. It's just basically reflection in the y-axis, and then this kind of sublattice phase that we already talked about. So what does the steady state look like? Well, again, the average photon number is always uniform. That's guaranteed. And the correlations are just determined by what the symmetry operator is. So the symmetry operator here just takes one site to its mirror image once I do this reflection. So if I now look at the pattern of correlation, so let's look at how the site 4, 1 is correlated with other sites on the lattice. This is what this is plotting here. Well, there's only one other site it's correlated with. It's the one that is basically its mirror image under this reflection operation. So this is sort of like a 2D generalization of that example from Zappilli and coworkers. The steady state is just a product of two-mode squeeze states. Every site is entangled only with its sort of mirror image. Okay, so that's all nice and well. It follows from the symmetry operator really easily. How do we make things a little bit wackier? Well, what if I put my coupling to dissipation on a site that doesn't have a lot of symmetry? Okay, and again, remember the key thing is there are many, many different chiral symmetries here, many different choices for the global wave function phase. The symmetry that's relevant is dictated by where you put the dissipation. So now, and let's just skip that, if I decide to put the dissipation up here, at the site 2, 4, right? And again, there's no dark modes in this system. You're guaranteed to get a pure steady state. The average photon number is completely uniform. Let me ask the exact same question. Let me single out one particular site. What sites is that one particular site correlated with, right? So what does this correlation matrix look like? It's basically correlated with half the other sites in the lattice. Okay, so there are many ways you could kind of think about it. I think no matter how you try to think about this, this is a pretty rich, complex, albeit Gaussian, entangled state. You have multi-mode entanglement here. Okay, so the upshot of all of this, when you break time reversal symmetry, so if you give me a Hamiltonian that has phases in it that I can't get rid of, but has this chiral structure, you really have the ability to generate a lot of different interesting entangled states, multi-mode entangled states, depending on where you decide to put the dissipation. So what these graphs are showing are basically, I'm plotting this correlation matrix. So each row, as I go through it, is kind of scanning all of the sites in the lattice. So if I put the dissipation at these sites with a lot of symmetry, I get this kind of pairwise correlation, right? So every site is correlated with its mirror image. Things look pretty simple. If I put the dissipation at a site without a lot of spatial symmetry, then all hell breaks loose, right? To some extent, everything is entangled with everything. Okay? So I want to get to the second story. So we've also there's clearly important questions to ask here, not just about the steady state, right? But we've heard many times in this workshop that dynamics are also important. So this is also an interesting model to investigate in a lot of detail. How long does it take to reach the steady state? And the fact that it's all basically linear dynamics with an impurity, right? So all the techniques you use to deal with impurity scattering in condensed matter, describing things with a T matrix, you can really use to get out all the timescales involved with the dissipation. So what's the bad news, right? It takes a long time to prepare this steady state. And that hopefully makes sense because you're injecting photons on one site. Those photons have to travel through the lattice, right? And you're not going to get the steady state until the photons actually make it everywhere in the lattice. So kind of well-known Lieb-Robinson bounds that come from just having locality in the way that your cavities are coupled. They'll also constrain how long it takes to prepare the steady state. The other thing you have to worry about is if you're not careful, there's xenophysics that can also be your enemy here. And what does that mean is, well, on some level, this engineered reservoir is measuring that one site, right? It's injecting photons, but it's also probing that site. If that coupling is too strong, the photons will never be able to leave that site, right? And that'll make it even harder for them to propagate and for you to reach your steady state. Okay, so yes, it takes a long time to reach the steady state. That time scale will scale with the number of sites in your lattice. If you have real dissipation, unwanted dissipation in the problem, there's going to be a competition between this preparation time scale and the natural damping in your system. So for this to work for a large system, you need fairly high Q objects to begin with. Okay, that being said, we still think there are many situations where having high Q objects to begin with is an easier, still difficult challenge compared to actually trying to control the dissipation everywhere in the lattice. Okay, so I think I have 5, 10. Okay, so good, lots of time. Okay, so I'll try to get to the second story, at least I wanted to tell you. So just to conclude this first story, again, revisiting this problem that a number of authors have already done a lot of really nice work on, we see that there's really some nice symmetry principles involved in having a single squeezed reservoir let you stabilize interesting states on a lattice. Okay, and when you also break time reversal symmetry, you can really get interesting, non-trivial steady states. The kinds of things we're thinking about now is, well, are these things you could exploit for interesting continuous variable quantum information applications? Are these kinds of states you could imagine doing something like Gaussian boson sampling with? And also, is this an interesting starting point for making the problem even more fun? And that is adding interactions, adding nonlinearity. Okay, so the second story I want to tell you in the last 5, 10 minutes is, what if we make things complicated not just by having many modes, but also by having interactions, Kerr interactions? Okay, so we always like to start simple. So many modes is going to be 2 modes, right? But we're going to talk about having 2 interacting modes. Okay, so the starting point for this second story is a really nice piece of physics that surprisingly was only really fully described in the last few years. Let's start with just a simple nonlinear one cavity problem. So what do I have here? I have a single cavity that's subjected to some resonant parametric or 2-photon driving. So there's an A dagger squared term in the Hamiltonian. There's no A dagger A term. That means I'm resonantly driving the system. And I have a Kerr interaction. Okay, so A dagger, AA. So this system, albeit despite the fact that it's nonlinear, it has 2 very, very simple exact eigenstates at 0 energy. Okay, or at 1 energy. And so basically, if you take a coherent state where the coherent state displacement squared is given by the ratio of the driving to the nonlinearity, that alpha and that minus alpha are guaranteed to be degenerate eigenstates, right? 2 lines of math to see that. So that means that the even and odd combinations of those states are also eigenstates. So this Hamiltonian has eigenstates that are even and odd cat states. Okay, so there's a lot of nice work from Goto, from Alexandre Blai's group, showing that you could harness this as a way of preparing cat states. That by adiabatically evolving the vacuum, which would be an eigenstate if I had no parametric driving, to one of these eigenstates when I have the parametric driving, you could prepare a given cat state. Okay, so what do we want to do? Well, we want a dissipative protocol, right? I don't want to do some slow adiabatic evolution. I want some clever dissipation that will just give me a cat state in the steady state. And I also want it to be multi-mode. So I want to actually think about not just one cat state, but imagine having 2 cavities. Imagine the 2 cavities are even remote. I love to be able to stabilize the state of those 2 cavities into some kind of entangled cat state. So for example, either both cavities are in an even cat state or both cavities are an odd cat state. Okay, so the question is, how do we do that? Is there some clever way of getting that? Okay, and again, because time is short, I'm going to kind of jump to the final simple answer that we think works for this. And so basic final scheme that we've come up with is what's sketched here. So I have two of these Kerr cavities. So each cavity has a parametric drive. So the cavities are A and B. Here are the two parametric driving terms. Each cavity has a Kerr interaction. That's these U's here. Thing that's different from that simple example is we have a detuning of the parametric drive. So if you want, there's an on-site energy in cavity A and cavity B. You see that in the Hamiltonian, there's no coupling between the two cavities. The only way the two cavities talk to one another is by having some correlated single photon dissipation. Okay, so in my master equation, I have a jump operator that involves the sum of A plus B. And again, that's not something that should freak us out. This is the kind of dissipator that you could realize just by coupling both of those cavities to a transmission line to a waveguide, by choosing the distance between the two cavities correctly. Okay, so what's the nice thing about this? This master equation has a unique steady state in the limit where lambda is sufficiently large. It's an entangled cat state of the form that I told you about before. It's also a really nice system because you can really find the steady state for all values of parameters analytically. Okay, so there's not a huge number of examples where that's possible. Okay, in 2 minutes, let me just try to give you some intuition as to why this actually works. So let's start with something simpler. If I had one cavity and I wanted to stabilize that one cavity in a squeeze state, how would I do that? So a squeeze state is the vacuum of some Bogolyubov mode, right? So what I need to do is basically cool that Bogolyubov mode. So how could I cool that Bogolyubov mode? Well, I could basically have another cavity, let's call it the D cavity, that is coupled to zero temperature dissipation. And then I could construct a very funny tunneling term that basically takes one of these Bogolyubov excitations, destroys it, and moves it into that second cavity. So then what would the dynamics of this be? Well, you keep removing these Bogolyubov quasiparticles from C, you put them into D, and then D has dissipation, it sort of vanishes. Okay, so it's easy to see that even if you don't do some adiabatic elimination of the D mode, this is going to give you a steady state where that C cavity is in a squeeze state. So how do I get, cats out of this? I need some nonlinearity. Well, let me just make this beta operator nonlinear, right? So the beta operator, it's a linear combination of adding and removing a photon. If I make the coefficient of removing a photon now itself depend on photon number, again, it's very easy to see that there are now two states annihilated by that operator. These two different coherent states, plus minus alpha, where alpha squared is just given by the ratio of this addition part and the coefficient of this removal part. Okay? So now, again, we have two degenerate steady states, right? I could take the even and the odd combination. Those would be cat states. How do I actually get what we really want? I don't want a single cat state, right? I want these separated entangled cats. Well, it's a well-known thing from many, many years ago in quantum optics. If you send one cat state through a beam splitter, you get an entangled cat state. So now I could imagine that this C mode and this D mode are actually linear combinations of two other modes, let's call them A and B, that are actually spatially localized. Okay? And then the only other thing, if I want a unique cat state, I need to somehow pick out the parity of, do I want alpha plus minus alpha, or the linear combination with the minus sign. So if I just actually interpolate between this beta operator and the original beta operator, that will give it to me. So at the end of the day, in this kind of setup, you have a nonlinear tunneling Hamiltonian that gives you the physics you want. When you change bases, so the dissipation here is local, right on the D mode. The dissipation now becomes non-local. The nice piece of math is that all of the nonlinearity in that tunneling Hamiltonian, becomes perfectly local. Okay, so in this new basis of A and B modes, the coherent Hamiltonian has no actual physical coupling between the two cavities. Okay, and again, in the limit of a large enough parametric drive, your steady state really approaches this entangled cat state where either both cats are even or both cats are odd. Okay, I think I'm pretty much out of time. Is that still 5 minutes? I don't want to eat into your lunch, so I might not take all of that 5 minutes. So you can sort of see, again, using this exact solution, how does this steady state evolve as a function of parameters. So I have two modes. If I wanted to plot the whole Wigner function, I don't know how to do that. I can take a cut through the two-mode Wigner function. And this is showing what basically happens as you change the value of the Kerr interaction. And what this shows is that you basically evolve from something that's looking like a squeeze state to a cat state. Okay, and again, we can describe this all with the exact solution. Why am I making a point of this? I want to try to connect the two stories that I've told you. The first story was all about just squeezing, no nonlinearity, a really nice way of using squeezing physics to get entanglement, Gaussian entanglement in a lattice. This story is telling us that, well, if you know how to get squeeze states, two-mode squeeze states, there are regimes where turning on interactions lets us continuously evolve or deform into some interesting non-Gaussian state. So something we're looking at now is basically finding a clever way of combining these two things together. OK, so I am not going to eat into your lunch, so let me just go to the conclusions. So hopefully I've told you a little bit about the work we've been doing in this area of reservoir engineering, these different approaches for trying to get experimentally friendly protocols in systems where either you have many, many modes that you're trying to deal with, and there your friend is really thinking about symmetry, or in problems where you have nonlinearity and you're interested in non-Gaussian remote entangled states. So with that, I will stop, and thank you for your time.
So thank you. I think there are plenty of questions.
Yeah. Are you conserving the number of photons, or is it with simply arbitrary particle number? So are you in a compact case or in a non-compact case?
Are you talking about the second scheme or the first scheme?
The first one.
So in the first scheme, photon number is not conserved, if I just think about the closed lattice system.
Yeah.
And that's from the squeezed reservoir, right? So if you looked at my jump operator,
Yep.
it was a linear combination of creation and destruction. Yeah.
No, this is really very interesting. And your chiral operator sigma, if you square that, or if you take the sigma times sigma complex conjugate, probably it's a minus unity, and this is indicative of a unitary symplectic, or a symplectic symmetry, as you would expect from bosonic systems with pair interactions. And therefore, this also tells you that this class of systems does have to come with this type of symmetry, and one can even relate fixed points to that.
Yeah, so there's a couple of points. So clearly, you can construct bosonic systems with this kind of pairing that don't have this symmetry. The thing that we always have in the back of our mind is we're more used to thinking about fermions. When the thing that this seems like it's closer to is particle hole symmetry and like a Bogoliubov-de Gennes type Hamiltonian. It turns out for bosons, though, it's really not the same thing, right? So a particle hole transformation for fermions will map H to H. Here, we get an extra minus sign. So commutation relations actually change the nature of the symmetry. We're interested in trying to understand that in a more complete way, but yeah, it was an interesting difference.
I think my question was just being anticipated by your words, because I was trying to think from the fundamental point of view. I understand that from the point of view of engineering, Hamiltonians, bosons have an extra advantage because they lend themselves to this optics type of manipulation. But thinking back to, you have free systems, Hamiltonian tight binding on lattice, and I was wondering why, or whether we could look into fermionic systems. I have looked at them quite extensively, and whether there are generalized symmetries that can be brought to bear in a similar way to what you had for chiral.
So I think it'd be interesting.
I think there are.
So
but,
you could probably ask exactly the same kind of questions in the fermion case. The thing that's interesting in the bosonic case is that you have something you just don't have with fermions, right? You have the existence of these squeezing transformations. So the implications of even, because again, normally you think about, okay, look, it's single particle physics, there's some quadratic Hamiltonian. Why would bosons versus fermions matter? And we've been really milking this a lot over the last year or two. When you don't conserve particle numbers, statistics really matter. So even these symmetries have different implications in the bosonic case. And physically, thinking about the existence of squeezing transformations is a way of right away seeing that there's something different here.
But pairing doesn't conserve classical number in
But it's a completely different Bogoliubov-de Gennes problem, right? There's no instabilities in a pairing problem with fermions, right? At the quadratic level. With bosons, all hell can break loose. You can have a parametric instability. Right there, you know that something is different. Yeah.
Fermions are compact and bosons are not.
Sure, yeah.
Michel? Yes, so Ash, in this beautiful work of chiral symmetry and reservoir engineering, do you think that there would be a minimal number of ingredients, maybe two sides and a little bit of nonlinearity that would transform your steady state into a dynamical state? Because right now you achieve a sort of steady state which doesn't have any dynamics. But
so by dynamics, do you mean like a non-unique like steady state, or do you mean
I would have not a single point attractor, but a limit cycle.
Okay, but when you say a limit cycle quantum mechanically, right?
Yes.
Do I
yes,
mean a single quantum mechanical state that resembles what I would think about as a limit cycle classically? Or do you mean actually a bunch, like some kind of multi-stability that would reflect?
No, not multiple stability, but just actually a dynamical attractor, something, a limit cycle. So basically the lattice would have a pattern, a configuration that would oscillate with time.
Yeah, so I think this question of kind of connecting like quantum states to limit cycles like has a classical limit cycles, right? There's a huge amount of literature on that. I think there could be some interesting connections that could be made here when you add the nonlinearity. I think in the case where it's just this squeezing that's coming in, I don't know if that's the best way of thinking about it. It's an interesting question.
As a reader of the experimental network work, one thing that they could benefit from even before this is probably better characterization of what the Hamiltonians they have made are. Can you use similar machinery to help give them those tools?
So I might flip your question around and say one of the nice things about thinking about symmetry considerations is that symmetry considerations can then tell you that you're insensitive to certain kinds of disorder or imperfections. So then even if you don't know your Hamiltonian well, or it takes you a lot of work to sort of know certain things, I can tell you which things you don't need to know well. So maybe that's not what you're looking for. Yeah, so yes, that would be a great tool to have, and maybe there's something to be done in that direction. It's not obvious.
I'm not sure if this is on.
I can hear you, yeah.
Okay. Anyway, so I'm sure you must have thought about this, but how much sort of other dissipation could you tolerate, right? I mean, you're not going to exactly have an A plus B dagger with some amount of imperfection, or in any of these things.
Of course,
so,
right.
So
yeah.
how much can you tolerate?
And it's this point that I sort of discussed, very quickly. So it's always a competition of timescale. So there's the bad dissipation that you're talking about, the internal loss that just wants all photons to leave. And there's some rate, right, that characterizes that. That's competing with this timescale for how long does it take the good dissipation to give you what you want. And the price you pay for just having one controlled dissipative site is that it's going to take a long time. So that's a timescale that's going to grow as some power law of the number of sites in your system. Okay? Once you have this recipe, though, and you want to do a little bit better, and you know about this symmetry telling you what the steady state is, if you now want to use 2 or 3 or 4 controlled sites, you know where to put them, and that can help fight that time scale. But that is definitely a concern, and so if you're really going to large system sizes, right, that puts a tight constraint on the internal loss of the cavities. Because again, this time scale has to be slow. To reach the whole lattice is going to take a long time. Yeah.
I have a quick question for the second part of the talk. Can I understand that one cat gets the stabilization of this joint cat? Is that because one of the cats is just dark and one cat is bright to dissipation in the transmission line?
Yeah, and that's something, so the fact that we just stabilize one cat is because that's what we chose to do. So if I go through this story here, at this stage, I could really stabilize 2 different cats, because again, there's 2 different coherent states that are sort of destroyed here. So what we did was we decided, well, let's just do one cat. It's an easier story. We added these detuning terms here. So the detuning terms actually give a preference for total even photon parity. If I didn't have the detuning there, you would have two steady states, which are spanned by some entangled set of entangled cats. And again, there are examples where having two steady states is actually better than having one, right? And thinking about how to exploit that is, something we like to think about more. But it's really the detuning terms here that give you a unique steady state. If you take that away, there's two entangled cat states that you can relax to.
So when you stabilize two orthogonal states and stabilize a sub-Hilbert space of your system, does it automatically imply that you will be able, with other forces, to drive the system in this sub-Hilbert space, and you won't be annoyed by the autonomous stabilization process?
Yeah, so that's an interesting question, and there's a lot of nice work coming out of Yale and from Maziar about this kind of quantum xenodynamics in a stabilized manifold. I think generically the same sorts of things should happen in the kind of manifold that we can stabilize here. It's a question on, again, how strong is the extra dynamics you're driving versus what's the characteristic rate of the stabilization. But there are regimes where you should get the kind of evolution you want, that you evolve within the stabilized manifold. You don't get thrown out to other parts of Hilbert space. Yeah, but it's very much like the questions that Maziar has looked at.
So I think we should thank Aashish, Clerk.